So in today's class, we're going to be looking at the next part of our topic here, which is going to be on mass transfer coefficient. Now, if you remember in our earlier classes, we did mention that we already discussed, saying that for us to know the mass transfer and diffusion process, we can model it using two models. The first model is using our diffusion coefficient, our DAB, and the second one is using our mass transfer coefficient. So in our previous classes, we have already looked at how we can define and how can we interpret the mass transfer coefficient when we are using our diffusion coefficient, our DAB or DBA or DB, right? That is our diffusion coefficient. In today's class, we're going to be looking at the second model, which involves the use of mass transfer coefficient. Now, first of all, we have to ask ourselves, why do we actually need, or why do we actually have these two models? So the simplest answer is that sometimes it depends on the situation. Now, both this model, diffusion coefficient and mass transfer coefficient, can be used to actually tell you about the mass transfer process that is happening, the diffusion process that is happening. But sometimes, due to your condition of the system, due to the circumstances, you can sometimes use diffusion coefficient and sometimes you have to use mass transfer coefficient. So firstly, if we were to ask, if you read any textbooks, most of people will agree that when you are using diffusion coefficient, it is more fundamental. Okay, but when we are dealing with mass transfer coefficient, it is more of an expert approximation, and it's also more practical. So depending on the case that you have, you can actually choose. So there is no one saying that, okay, mass transfer coefficient model is better than diffusion coefficient model or vice versa. So the only thing that you need to know is that it depends on your condition that you have. Depends on the process and the process that you are dealing with. So in mass transfer coefficient, the main reason why you want to use mass transfer coefficient as opposed to diffusion coefficient is that the equation for diffusion that we have been using so far, right? If I were to write here our Fick's law, right? It's saying that JA, our flux, is equal to negative DAB dCA over dZ. Okay, so in order for you to define the value of flux JA or the total flux NA, you need to know the diffusion coefficient, you need to know the differences in your concentration, and also you need to know the length or your path of your diffusion. You need to know your delta Z. So when we are dealing with mass transfer coefficient, sometimes we don't have this value. We don't have this dz value. So the equation for diffusion developed so far, that we have been using so far, can only predict steady state mass transfer coefficient, provided that we have the film thickness, right? We have our zt or dz or delta z value. However, in most cases, this zt value is not known, and one of the reasons is that because of the turbulent flow that we actually want. Why you want turbulent flow? Because if you have turbulent flow, it can increase the rate of the transfer per unit area and also to increase the more interfacial area. So as compared to laminar flow, turbulent flow is desired when we have our separation processes. So when we have turbulent flow, there will be more mass transfer happening, and if more mass transfer is happening, it is more beneficial for us as compared to laminar flow. So when we are dealing with turbulent flow, it is very hard for us to actually know the value of the thickness of the path, the length of the diffusion path. So when we are dealing in turbulent flow, we define a new constant, which is known as our mass transfer coefficient. And the symbol that we will be using is K. Okay, this is the symbol for mass transfer coefficient. So we can define the mass transfer coefficient. K is equal to rate of mass transfer over area times the concentration difference. So this is basically the definition of mass transfer coefficient. And some reference books also say that this model is simpler and more appropriate and is especially useful when only average concentrations are involved. So meaning the same thing here, that when we only know the concentration and we still want to find the rate of mass transfer, when we still want to find the flux of mass transfer, molar flux or mass flux, it is better for us to use this K value. Now, this K value, if you see here, right, this is the definition of K. K is equal to rate of mass transfer over area times concentration difference. Now, since we know that our flux, our J here, can be defined as rate of mass transfer over area. Now, if I were to write JA, the unit is usually mole per meter squared second, right? So rate, this is our rate, mole per second is a rate over area. So that is the, so you can see here, this whole thing is actually our J, right? Rate of mass transfer over area is J. So based on this definition of mass transfer coefficient and based on our definition of our flux, whether it's molar flux or mass flux, the unit for J, we can say that the Kc here, the K, we can define it as flux over concentration difference, because we already know that this value, the whole thing here is our J. So we can say J here, and then the concentration difference can be our delta C. So I can write here again, K, the general equation is equal to J over delta C. Okay, so this is the general equation for K. How we can calculate the value of mass transfer coefficient. Now, this thing is a little bit different as compared to our diffusion coefficient. Now, the diffusion coefficient, we say DAB, will have a unit of either area over time. So usually we use cm squared over second, right? All our diffusion coefficient, our diffusivity will have this unit. But for K here, it is a little bit different. Now it depends on what kind of, what are you defining this K. Okay, so for example, now when we have Kc, okay, when you have small k and subscript c here, meaning that you are actually defining this K in terms of concentration. So Kc here meaning that mass transfer coefficient in terms of the concentration. So when you have mass transfer in terms of concentration, this is the formula, Ja divided by Cai minus Ca. So this is basically your delta C. But since this is in terms of concentration, the unit will be same as unit of velocity, which is meter per second. Okay, how do you get this unit? You can just do unit cancellation. So for example, for this one, let me just try to, I can put it here maybe. So I know that for my Ja, I know that my unit is going to be mole per meter squared second. Okay, that is my unit of Ja. Now I know that I will have 1 over, now the unit for concentration usually is going to be mole per meter cube. Okay, so when you have this, if you cancel out, mole will cancel out with mole, meter squared will cancel out with meter cube, and then you will be left with meter per second. Now this is the unit for Kc only. Okay, so you cannot say that K has a unit of meters per second. Kc has the unit of meter per second. Kc meaning that mass transfer coefficient in terms of concentration. When we are dealing with mass transfer in terms of mole fraction in vapor phase, so we write K1. So that is why you need to know Like in our earlier classes, we already defined C is for concentration, Y is mole fraction in gases or vapor phase, and X is mole fraction in liquid phase. So when we say that we have Ky, so automatically when you look at the symbol, Ky is actually equal to Ja over Yai minus Ya. Again, this is your delta Y, but this Ky is your mass transfer coefficient in terms of mole fraction of vapor phase. So the unit will be mole per meter squared second. Now if you see here, this is actually the unit of our flux, right? Mole per meter squared second. So why do we get this unit? It is simple because your mole fraction does not have any unit. Okay, so this is as simple as that. So you can, the same way you can find the unit for Kx, which is going to be the same, right? Because mole fraction, again, whether it's liquid phase or gas phase, it does not have any unit. So you have to be careful when you are solving this using these equations, the unit for K. And then Kc can also be correlated with Kx and Ky. So if you have the value of Kc, you can actually find the value of Kx and Ky by using either the molar concentration, the mass concentration, our rho m here, or you can also use our EV equal to nRT for our gas phase, right? And then we can also use this is your average molecular weight of the fluid. So there is a relationship between Kc and Ky and Kc and Kx. And then when we look at our equation just now, when we look at our this is our Fick's law, right? This is our Fick's law. So basically what we are trying to do here is that we want to find a relationship between our Fick's law and our Kc value. Now if you look at here, if you do substitution, right, you know that we already defined that Kc is equal to Ja over Cai minus Ca, which is your delta C. And we already know that we already defined our Fick's law is equal to Ja is equal to dAb Zt Cai minus Ca. Now if you see here, I have removed the negative sign because I have integrated into this part of the equation. So if I substitute this whole thing here, I substitute this with this equation, I'll get an equation like this. Okay, and then I can know that this one I can do unit cancellation. So the thing I left is here is that I can say that my Kc here is actually equal to dAb over Zt. So this is a relationship that we can develop. Okay, so if let's say we are asked to find the value of Zt, and we are only given the value of Kc and we are only given the value of dAb, we can actually find the value of our diffusion length by using this relationship. Now this relationship is actually a basic relationship. To get a more accurate relationship between the Kc and our dAb, between our mass transfer coefficient and our diffusion coefficient, scientists and researchers before this have actually developed what we call as mass transfer theories. Okay, so these mass transfer theories usually deals with the relationship between our mass transfer coefficient and our diffusion coefficient. So some of the popular mass transfer theories, for example, is film theories, two boundary layer theories, two film theories, and also penetration theories. So if you are interested to learn more, to get a more understanding on this, how Kc is related to our diffusion coefficient and how these theories actually explain this, you can always refer to our reference book.